Today, we are going to pull back the curtain on one of the most critical but maybe least understood parts of your computer, the CPU cache. You can think of it as the unsung hero, the secret weapon that makes everything feel snappy and fast. Honestly, without it, even the most beastly processor would just grind to a halt.
So to really get a handle on this, here's our game plan. We'll kick things off by understanding the core problem, what I call the great speed gap. Then, we'll look at the brilliant solution with an analogy, the CPU's pockets. After that, we'll see how that builds into a whole hierarchy of memory, tackle the tricky problem of keeping it all in sync, and finally, we'll tie it all together to see how this stuff makes our computers smarter, not just faster.
All right, let's dive right in. We have to start with the fundamental challenge, the one big hurdle that every single modern computer has to figure out how to jump over.
You know, it's a crazy paradox when you think about it. We have these processors that can do billions with a B, of things every second, and yet a huge chunk of their time is spent doing, well, nothing. Just sitting there, tapping its fingers, waiting for data.
And here is why. Just look at the insane difference in speed. For a CPU to grab some data from its closest, tiniest bit of memory, the L1 cache, it takes less than 1 nanosecond. But for it to go all the way out to your main system RAM, we're talking 70 nanoseconds. That's 100 times slower. This gap is what engineers call the memory wall, and it is the single biggest bottleneck in computing today.
So how on earth do you solve a problem like that? I mean, you can't just make RAM 100 times faster. It'd be wildly expensive and complicated. So instead, engineers came up with a much more ingenious solution.
I absolutely love this analogy I found on Reddit because it just nails it. Imagine you're a window cleaner on a massive skyscraper. The tools in your hand, that's like the data your CPU is using right this second. It's instant. But you can't keep climbing all the way down to your truck on the street every single time you need a new squeegee or a different cloth. You'd get absolutely nothing done all day.
And that, right there, is exactly what CPU cache is. It's the window cleaner's pockets. It's a small, super-duper fast little holding area for the data the CPU is probably going to need next. This way, it avoids that long, slow, painful trip all the way down to the truck, which is our main memory.
But here's the thing. It's not just one big pocket. Oh no, the system is way more sophisticated than that. It's actually a whole pyramid, a hierarchy of memory, and each level has its own special job.
So when the CPU needs something, it follows a very strict checklist. First, it checks the L1 cache, its immediate pockets. If it's not there, that's called a cache miss. It looks in the L2 cache, which you can think of as a personal toolbox. Still no luck? It moves on to the L3 cache, which is like a bigger shared tool chest. And only if it strikes out on all three does it finally give up and make that long, slow trip down to the truck, our RAM.
And this table really lays out the fundamental trade-off. L1 cache is tiny, but it's unbelievably fast. As you go down to L2 and L3, they get a lot bigger. They can hold way more stuff, but they also get a little bit slower with each step. It's this constant balancing act between size, speed, and of course cost.
Now, this whole system works perfectly for one processor core, one window cleaner. But what happens when you've got a whole team of window cleaners, multiple CPU cores, all working on the same skyscraper at the same time, each with their own pockets and toolboxes? Things can get messy.
This is where a really important idea called cache coherence comes into play. You can think of it as the rule book that makes sure every single core is working from the same, most up-to-date set of blueprints. Without it, you'd have total chaos. Let me walk you through a quick example. So, let's say one core, we'll call it Core A, grabs a piece of data. It now has a copy sitting in its lightning-fast L1 cache, and the value of that data is 5.
Okay, but now, at pretty much the exact same time, another core, Core B, needs to change that exact same piece of data. It does some work and updates the value to 10 in its own local cache.
So, here's the million-dollar question. What happens now? If we don't have a coherent system, Core A is completely in the dark. It has no idea Core B just made a change. It's still looking at its old, stale copy, where the value is 5. And if it uses that old data for a calculation, you get a wrong answer, which can cause programs to crash or, well, much worse. So these coherence protocols are like a communication network, constantly shouting between the cores, either telling Core A, hey, that copy you have is garbage now, or even better, just updating it with the new value of 10. It makes sure everyone is on the same page.
Now, this isn't just some abstract computer science theory.
The design of the cache system is the real battleground where chip designers are squeezing out huge performance gains. And let's look at a perfect real-world example of this.
Let's take AMD's new Zen 5 architecture. A lot of the biggest improvements have nothing to do with just raw clock speed. Look at this. They doubled the bandwidth, basically the size of the data highway, to the L1 and L2 caches. This lets the CPU shuttle data back and forth twice as fast. They also improved something called branch prediction, which is a fancy way of saying the chip got a lot better at guessing what you're going to do next so it can have the right data already warmed up and waiting for you.
And the result? You can actually measure it. These cache improvements lead to a 16% average increase in something called instructions per clock, or IPC. In simple terms, that means for every single tick of the processor's clock, it's getting 16% more real work done, not because it's faster, but because it's smarter and spends way less time waiting around.
And check this out. For really data-heavy stuff, like AI or big scientific calculations, the gains are even more massive. Because those jobs can really use those bigger data highways they built, they see performance jumps of up to 35%. That's huge. So I think the big takeaway here is that we kind of have to redefine what performance even means. It's not just about the gigahertz number on the box anymore. Real, tangible performance comes from the smarts, the efficiency of the whole system. And at the heart of that efficiency is a clever cache that is an absolute master at avoiding waiting.
Which, of course, leaves us with one last really interesting question to chew on. The cache was invented to solve the memory wall bottleneck. But in technology, as soon as you solve one problem, another one always seems to pop up. So what do you think the next great challenge for computer architects will be? And what kind of clever new toolboxes will they have to invent to solve it?